Welcome back to the Math Professors. We do videos pertaining to algebra, pre-calculus, statistics, the calc sequence, and so on. Please consider sharing, liking, and subscribing to our videos so we can provide more of this free content. So today I'm going to cover a binomial probability distribution. So we're going to start out with the requirements for binomial probability distribution. So first, the requirements are we have a fixed number of trials. The trials must be independent. Each trial has only two outcomes. These outcomes are success and failure. And the probability of success has to be the same for each trial. And here's some notation. Capital S is going to be success. Capital F is going to be failure. The probability of success is going to be little p. And the probability of failure is going to be little q, which is going to be 1 minus little p. Since there's only two outcomes, those probabilities have to add to 1 because it's a probability distribution. So the number of trials is equal to n, and then our formula for a probability distribution is given by this, is n choose x times the probability of success raised to the x power times the probability of failure raised to the n minus x power. So I'm going to give us a basic example that we did in a previous video, and I really just want to kind of prove that this probability distribution formula works. And then I'm going to do an example that's far more complicated to really show where these things actually come from. So the first I'm going to talk about is the number of girls that we talked about in the previous two videos. So let's let x be the number of girls, and then if I want to find what's the probability of say 2 girls. So what we want to do is we want to look at the sample space. So let's do this. So previous videos we had a sample space of boy, we had girl, we had boy, and then we had girl, boy. Now I wrote this over there, the 2 girls part. But really, if I want to find the probability of having 1 girl, what we know is going to be, this means that the probability of having 1 girl is going to be how many times you see 1 girl. So this is 1 girl, this is 1 girl. So we can see that this is going to be 2 out of 4 times. These two outcomes will give you 1 girl. So we can see that there's a 50% chance of getting 1 girl. So if I want to look at this probability distribution, what I'm really asking for using the formula is I want to find p of 1. Well, let's make sure that this makes sense. So if I'm asking for a fixed number of trials, what I'm saying is, this is family of size 2. Well, their children are size 2. So I'm going to have 2 children, so there is going to be 2 events. Are the events independent? Yeah, if I get a boy in the first event, doesn't really mean I'm going to get a boy or a girl in the second event. So these probabilities are not affected by the previous one. Each trial has only 2 outcomes. We consider success and failure. Now, since I'm asking for the probability of the number of girls, in this case, girls is going to be considered success, and then the boys would be considered a failure. We're not saying there's a plus or minus or a positive or negative idea to these things. It's just what we call success, what we call failure. It's asking, success is what I'm actually asking about. The probability of success must be the same for each trial. Well, I know the probability of having a girl is going to be 50% every single time. So that's why this is true as well. So that's why this is considered a binomial distribution. So let's kind of use this formula. Well, what I know is that using this, I know that there's a fixed number of trials, and that fixed number of trials means n is equal to 2. There's 2 children. The trials must be independent, so the probabilities don't affect each other. The trials must only have 2 outcomes, back to that. I'm asking now for the probability of just having 1 girl. So in this case, I'm asking for just x is equal to 1. What I know is the probability of having a girl is going to be 50%, which means the probability of having a boy is also going to be 50% because q is going to be 1 minus p. So this is going to be 1 minus 50%, which is 50%. Now I have, I have my n, I have my x, I have my p, and I have my q. I know all these things. So if I want to find p of 1, well, p of 1 is going to be equal to n is 2, choose x is 1, times the probability of having a girl, which is going to be 50% raised to the first power, times the probability of having a not girl, or in this case a boy, is going to be 50% raised to the 2 minus 1. And if when you plug this into your calculator, you're going to get this exact same probability right here, you're going to get this, which is 0.5. So what I want to do is I'm going to give us a much more complicated situation so then we can kind of see exactly how this thing is determined. So let me pause it. I'll write up an example and then we'll work through it. All right, so here is my example. It says consider taking a 4-question test that is multiple choice. Each question has choices A, B, C, D, and E. What is the probability of getting 3 of the 4 questions correct? And what we're going to do is we're just going to assume that we're guessing and we have no previous knowledge of what's on there. So just by guessing, what's the probability of getting 3 out of the 4 questions correct? All right, so in order to do this, let's kind of talk about really the probability of getting a question correct. So then I can kind of talk about the probability of getting multiple questions correct and 1 question wrong. So if I want to find what is let's say the solution here. Let's do it in parts A. So find the probability of a success. So what's the probability of C and the probability of getting something wrong? So we know the probability of C. Well, if I have, let's kind of just go over here. If I have like an A, a B, a C, a D, and an E, and when you're talking about multiple choice, they give you these circles, and then they ask you to fill in one of these circles. And what I know, let's just assume that in this case, letter D is correct. So we can see there is 1 correct and 4 wrong. So 1 correct out of a total of 5. So the probability of being correct is going to be 1 out of 5, or we can say that this is 0.2. Therefore, the probability of being wrong is going to be 4 out of 5, or 1 minus this, which is going to be equal to 0.8. All right. Now B, let's find the probability of getting something that is let's say 3 correct and 1 wrong in that particular order. So really, what I want to do is I want to find the probability of say correct, wrong. So in order to find this probability, really what this means is we have 4 events happening here. This is the probability of getting the first one correct, and the second one correct, and the third one correct, and the last one wrong. Now, since this is a probability distribution, I know, since this is a binomial probability distribution, we know that the events are independent of each other. So this is just multiplication without worrying about dependence. So this is going to be the probability of C multiplied by the probability of C multiplied by the probability of C multiplied by the probability of W. So when I multiply these things together, the probability of C is going to be 0.2, the probability of C is also going to be 0.2, the probability of C is going to be 0.2, and finally the probability of being wrong is going to be 0.8. So this is going to give me, let me calculate this, 0.0064. Now what we know is, what are the other ways this can happen? So C, what are the other orders to get 3 right, 3 correct, and 1 wrong? So let's start out with what we have here. So we know that one way to do this is correct, wrong. So other ways we could do this is I can move the wrong here, so I could do correct, wrong, correct. Or I can move the wrong here, so I can have correct, wrong, correct. And then finally we can have the first one correct and the last one's wrong. So these are the different orders to get correct, wrong. So really what I want to do is I can finally answer this question. What is the probability of getting 3 right and 1 wrong? Well, D, we know that the probability of, let's say 3 correct and, let's clean that up. 3 correct and 1 wrong really would be the probability of CCCW or CCWC or CWCC or WCCC. Now, if I was going to ask what's the probability of, say, any one of the other ones, I know the probability of this one. We just calculated it. But what if I wanted to find the probability of this one? Let's just do a quick investigation, and then then we'll just kind of jump to the end. So if I want that probability, what I know is it's the same thing as this except reordered. That instead of the wrong being here, the wrong is going to be here. So this is going to be 0.2 times 0.2 times 0.8 times 0.2. No matter what, we are going to get 4 products here where I'm going to have 3 0.2s and then 1 0.8. And since multiplication is commutative, it doesn't really matter where that 0.8 is. You know, this probability is still going to be the same thing as this. So when I do this OR statement, I'm just going to be adding 4 of these things together. So the reason why I'm doing adding is because OR statements are addition statements, and there is no overlap here. These are disjoint. So this is going to be the probability of CCCW plus the probability of CCWC plus the probability of CWCC plus the probability of WCCC. And each one of these things is going to be equal to 0.0064 plus 0.0064 plus 0.0064 plus finding 0.0064, which is going to give us 4 times that, which is going to give us 0.0256. So pretty unlikely for us to get 3 out of 4 just by guessing. Now I do know that this is a binomial probability distribution, and kind of filling out the letters, I'm a little out of room, but I don't want to lose this. This information is useful for understanding where a probability distribution comes from. So when we did this, we have, P of x is equal to n choose x times p to the x times q to the n minus x. Now remember that p is the probability of being correct, and q is the probability of being wrong. Now I'm asking for 3 correct and then 1 wrong. What we can see here is that this is going to be equal to, we'll worry about the n choose x. Let's write this here and kind of time around. So this is n choose x. Notice I want 3 answers correct, and we can see over here that no matter what it was, it's this exact same thing except these things are ordered. What I'm going to have is, regardless, I'm going to have that 0.2 cubed. I'm going to have 3 factors of 0.2. And right here I'm going to have, 1 factor of 0.8, and we can see that this is 0.8 to the, there are 4 questions, and then 3 of them are going to be correct. So this gives us a power of 1. So, this is that n choose x. So this is 0.2 cubed times 0.8 to the 1. And we can see that. I have 3.2 factors and then 1.8 factor, and it didn't matter what order I was going to put these things in. I was going to have 3 of these and 1 of these. Now, what I do know is that there were 4 of them in total because there are, since the probability doesn't matter regardless of order, I really just need to know how many of these things are going to give me the same probability. So it's going to be the combination of, 4 choose 3. So this is going to be 4 choose 3. And when we calculate 4 choose 3, what I'm actually going to get is this is going to be 4 times, that's what 4 choose 3 is, 0.2 cubed times 0.8 to the 1. So that's why I have 4 of these, right? This is 4 times that. So this is 4 times that 0.0064. That's what this is going to give us. 0.0064 times 4 is going to be equal to that 0.0256. So this is really where the binomial probability distribution formula comes from. This comes from this idea. It really is a combination, or a matchup of both and or statements. So it's pretty clever. So again, consider liking, subscribing, and sharing. Thank you.